I want to start with what I hope is going to be the most boring part of this presentation. I will introduce myself. So, my name is Vladik Khononov. I came here from Israel. I work in our industry for almost 20 years now. I worked in roles ranging from webmaster to chief architect. And software architecture for me is not just a job, but it's also my hobby. Yeah, I'm a nerd and I love software architecture. I love researching the stuff, blogging about it, speaking at conferences like this one. And today I want to talk about software architecture from a bit of an unusual point of view, from point of view of testing. And I want to start with a short story. About 9 years ago, my team had inherited a project that passed many, many hands. And each pair of hands made this code base even worse than it has been before. So over the time, the project became a big pile of code. It was so bad that at some point it was almost impossible to even look at it. Your eyes almost bled just from the sight of those methods and classes all spanning hundreds and even thousands lines of code. And of course, the state of this code base didn't improve a bit after each new release. It just degraded more and more. So the whole team hated it, I hated it. So no one wonder when a friend of mine called me and offered to join him as the chief architect of a new startup company, I agreed just like that. And not only it was a greenfield project where everything was implemented from scratch, but it also gave me the freedom to make all architectural decisions. And to prepare for this adventure, I've got lots of books on patterns, domain-driven design, and software architecture. In general, I read all of them, and I promised to myself that this project is going to be designed by the book, following all the practices and principles of clean code and modular architecture. So I invested lots of effort looking for that perfect architecture. And my goal was to design it in such a way that would allow us to quickly implement new features, that would alleviate the process of introducing new engineers to the code base, and of course the architecture had to support automated testing of all business logic. And even though things looked quite promising at the beginning, not everything went as smoothly as I hoped it will be. So the more functionality we added to this project, the more its architecture had to change. We had to migrate patterns, libraries, frameworks, and even we had to change programming languages. And to be completely frank, each such change had a negative impact on my ego. I spent again lots of effort and I hope that this project is going to be perfect. But it looked like it didn't stand the test of time. Now, that was what I thought back then. But today, 8 years later, my point of view on this subject has changed a bit. Because you see, over the years, our business has been continuously changing and evolving. The company learned from its mistakes, its business processes were optimized, and not only that we evaluated new profit opportunities, a couple of times we even changed the business domain of the whole company. We completely changed our sphere of business. And also during those 8 years, our industry saw lots of technology related changes. We've seen patterns, architectures, and even whole infrastructures come in and out of fashion. And of course, we could not predict all these developments back then. We had to make some guesses. We just call them assumptions. We had to test those assumptions out, and in some cases, we had to change our minds later. Eventually, today, that system serves in production for over 7 years. And during these years, the R&D team had changed many times. The turnover of developers in Israel is crazy. And not only that we suffered from this turnover, but we even moved the engineering center from Israel to other countries. But despite all these challenges, the codebase didn't degrade into the legacy status. It is still in a pretty good shape. And that's not because our initial architecture was perfect. No, it was far from it, trust me. However, re-evaluation of design decisions and constant evolution of the system's architecture allowed us to keep it in shape all these years. And in this presentation, I want to share what we learned about the testing aspect of software architecture. I'll talk about how can we test it, how to detect weak spots that need reinforcement, and of course, how to do it before the system becomes a big ball of mud. And finally, of course, I'll talk about how we can automate some of such architectural tests. But first, I will have to torture you a bit with some theory. So let's talk about software architecture. Why is it important? Why can't we just hack some solution and deploy it to production? Why do we even need to care about software architecture? And overall, what is software architecture? So when pondering this question, usually two quotes come to mind. The first one by Ralph Johnson, who said that architecture is about the important stuff, whatever that is. And the second one by Martin Fowler, who says that software architecture is those decisions which are both important and hard to change. Now, both these authors stress the importance of architectural decisions. And they are important because a thought-through architecture is essential for delivery of the system's functional and non-functional requirements. And since today software systems are an integral part of modern business, software architecture becomes essential for competitiveness of the companies that are using that software. But as Martin Fowler had said, architectural decisions are hard to change. For example, in the startup company that I told you about before, we had to choose the infrastructure we are going to run on. Are we going to run on self-managed servers or should we go to the cloud? And again, 8 years ago, this decision wasn't trivial. Also, what about the database? All of us had experience only with relational databases. But it was quite tempting, to explore the brave new world of NoSQL databases. We had to decide how to architect this solution. Should we go with traditional monolithic style or implement the system with SOA? And SOA, that's what they called microservices back then. And of course, we had arguments about languages and frameworks, and these arguments almost led to religious wars in our company. So all these decisions directly impacted our ability to deliver business goals. And that made those architectural decisions not only hard, but also full of risk, because one wrong decision and the complexity of the whole system would skyrocket. Therefore, in my opinion, the goal of software architecture is to manage the complexity of the systems that we are building. And usually we manage this complexity by decomposing systems into sets of interconnected components, modules. These modules can take different forms. They can be classes, namespaces, services, or whole systems. But at whatever level they are, modules make it easier to comprehend the responsibility of each module and how it interacts with the rest of the system. Modularity also alleviates reasoning about the whole system, how the system works, and what are its goals, what problems that system is supposed to solve. And from the technical point of view, modules allow us to limit the scope of those architectural decisions. For example, each component can use whatever database is more convenient for its own needs. And if there is a need to migrate from one database engine to another one, that change will affect only the module itself and not the whole system. So actually, modules divide complexity of the system into two types. The first one is local complexity of each component. And this notion of local complexity is easier to demonstrate with a simple heuristic. So let's say we have some module and we want to evaluate its complexity. So all we have to do is to ask ourselves, if we were to introduce a junior team member to work on this module, how hard or how easy would it be for that junior team member to comprehend what this module is supposed to do and how is it implemented? In our case, in our company, we had a module that was responsible for calculating commissions for sales agents. So all of its public APIs methods were related in one way or another to those commissions. And because its business scope was quite limited, its implementation was not really complicated as well. On the other hand, we had a module that at one stage had to manage advertising campaigns, it had to manage creative materials, and even take care of the company's finances. So in the second case, forget about the junior developer. Sometimes I had no clue what this thing is doing. So obviously the local complexity of the second module is way higher than of the first one. And the second type of system complexity is global complexity. It reflects the level of interconnectedness of the system's components. So when the global complexity is low, it is easier to understand the role each component plays in the system, and when a component has to change, the change will have a low impact on the rest of the system. For example, if this system that we see here on this slide, if it has a relatively low global complexity, then this one is more complex. Here we have much more connections between the same number of components. So a change in, for example, a change in the public API of one of those components will have a larger impact on the whole system. Hence, the composition of a system into modules or defining the boundaries of those modules is a key architectural decision. It allows us to manage the local complexities of the components and the global complexity of the whole system. That's why, in my opinion, Ruth Malan gave a much more clear answer to the question of what is software architecture. She says that it is inherently about boundaries. What's in, what's out, what spans, and what moves between those boundaries, and what trade-offs we are making when choosing the boundaries. So software architecture is about defining the right boundaries for the modules, for the components of the system. And over the last few decades, our industry had tried quite a few different ways of, looking for those module boundaries. In the days of waterfall, we had the big design upfront approach, when we tried to plan all the tiniest details of the system way before beginning to even working on it, before writing a single line of code. So usually such efforts didn't end well. It resulted in a very rigid design that fell apart quickly. Usually when one of the assumptions was proved wrong, suddenly the whole design didn't make much sense anymore. When Agile came along, many used it as an excuse to do away with architecture, instead just building something that works here and now. And it even seemed productive initially, but after some time and architectural hangover came along, and suddenly the system became impossible to evolve and to maintain. Next, software architecture became responsibility of someone in the role of software architect. And this approach has a few major flaws. First, architectural decisions can become personal. If something is wrong and has to be changed, it can take some time for the architect to acknowledge it. As a result, the evolution of the system will drag on, and it will be executed when it's or late or even too late. The second problem is when we divide the roles of designing the system and implementing it, we're creating a situation with lack of feedback because architects usually don't eat their dog food. If there is an issue with a design which is discovered only while working on the system, they have no way to know about it. And finally, the approach of evolutionary architecture started gaining traction lately. And the core idea of evolutionary architecture is that architecture should evolve incrementally on par with the system itself and its business domain. The goal of this approach is not merely changing the design, but adapting it to the ever-changing business needs. Because as a matter of fact, a system's design is going to change, whether we want it or not. The problem is it's going to change for the wrong reasons. Because software, as all systems, is subject to entropy. No matter how tidy and clean it has been in the beginning, without proper maintenance, over time it will decline into chaos. In other words, we all had encountered some really messy code bases, right? But none of them started with engineers sitting around and planning how to implement this project in the worst way possible, right? No, that's not how things are done. Usually, we want to be proud of our work. We want to do the best job possible. However, the hardest part of project design, of architectural design, is not greenfield projects, but when those greenfield projects become brownfield, when the project is already in production and its requirements are changing and we have to introduce new features. And if we won't properly manage the complexity of the system at that stage, it will eventually decline into disorder, into chaos. At some point, it will become, the legacy code that everybody loves to hate and just dreams to throw it away one day and rewrite it from scratch. And of course, this time we are going to do it right. So to prevent such a degradation, from time to time we have to shake up the system. We have to identify those weak spots and reinforce them over time. But the later we do it, the more expensive this is going to be. So how do we detect those architectural debts? And for that, let's talk about testing. So traditionally, we've got two types of tests. We have functional testing for verifying the software's behavior, and we have non-functional testing for verifying the system's properties. For example, its ability to scale, its level of security, or its usability. I think we should employ a third type of testing, architectural tests, for verifying the system's local and global complexities. In other words, testing how well do the system's modules fit its business requirements. And we saw that when the boundaries are optimal, it's easy to find a way around the project. It's evident what the software is supposed to do and how it works. The system is also easy to maintain, evolve, and it easily supports new business needs. But On the other hand, when the boundaries are incorrect, we get the opposite. The system is hard to change and it's hard to comprehend. And we even have a pattern for such system design. We call it the big ball of mud. So if you look at Wikipedia, it says that a big ball of mud is sloppy duct tape and spaghetti code jungle. This system shows unmistakable signs of unregulated growth. Information is shared among distant elements of the system, and often to the point where nearly all the important information becomes global or duplicated. Almost everything in this definition screams high global complexity. Now, it's quite easy to understand whether or not a system is in the state of a big ball of mud. If you look at the code and your eyes bleed, yes, that's a big ball of mud. That's easy, but it's also too late, it's useless. We need to identify architectural shortcomings at earlier stages, because the sooner we diagnose the problem, the easier it's going to be to fix it and to stop the formation of that dreaded big ball of mud. And the good thing is, when a system has architectural issues, we can learn about them from a variety of sources. We just have to be conscious about it. For example, from the developer's point of view, let's say that we have to implement a new feature, but it's unclear to which module this feature belongs. Or when each new feature always affects multiple modules. Also, let's say we have to change an existing functionality, but the change either affects multiple modules explicitly or implicitly affects others, seemingly unrelated parts of the system. In all those examples, we had cases of high global complexity. In other words, the modules are tightly coupled to each other, and the change in one component affects many other unrelated modules. Another evidence for high global complexity is the difficulty to unit test the system. Units are literally spread among multiple modules, and unit tests turn out to be useless spider webs of fake objects that don't really test anything. And actually, here I want to quote Michael Feathers. I really like this tweet that he published not long ago. He says that unit tests are tests of modularity. And I don't know about you, but this simple sentence is brilliant, really, because I've encountered many teams saying that, okay, we gave up unit tests because they are too fragile. We change our business logic one bit, and then all the tests are failing, and we have to go and fix them, and we spend much more time fixing the tests than implementing new features. Well, usually as an alternative, they pick end-to-end tests, which are testing the whole system end-to-end and just ignore the modules. So in this case, the module boundaries are wrong. The global complexity of the system is way too high. QA engineers can spot high global complexity, for example, when some existing functionality changes, but the change in the implementation didn't affect the whole system. That means that the business logic is duplicated across multiple modules. And in most cases, when such bugs are observed, the developers didn't even expect the logic to be duplicated. On the other hand, having to execute too many regression tests may be caused by high local complexity. It usually happens when something changes, but no one is confident about what parts of the system are going to be affected by that change. Therefore, the whole system has to be checked. So when local complexity is high, we have too many regression tests, and it's a sign that maybe the system's architecture can be improved, for example, by dividing some complex module into multiple smaller and simpler modules. Database administrators can also identify forming a big ball of mud. For example, if the same data is duplicated in multiple data stores, but it's impossible to identify which one of them is the source of truth. In other words, when the data goes out of sync and it's hard to identify which one of them is correct. It probably means that, again, the business logic that manages that data is duplicated between different modules. Another example would be when a single user operation affects data in multiple modules, and it's physically impossible to guarantee strong consistency of those changes. The business logic requires strong consistency, but the system can only support eventual consistency. In both these cases, the global complexity is too high. And finally, even operations people can be affected by bad module boundaries. Today, the lack of DevOps culture is by itself a strong signal that something is probably wrong with that architecture. And if the deployment process is too complex and risky, in many cases it indicates that the global complexity of the system or the local complexity of some of its components are too high. For example, if you change one module, but once you do it, you have to redeploy all the rest of the modules. Again, very high global complexity. So as you can see, everybody suffers from bad modules. And a person in the software architect's role cannot be in charge of it solely, because they don't necessarily experience all these issues. They don't have to eat their dog food. Hence, to keep a system's architecture in shape, we need continuous feedback from all the people working on the system. Every stakeholder involved on a project has to participate and to raise issues that they observe. And this brings us to good news, bad news. Bad news, this approach requires lots and lots of discipline, and not everyone has it. Good news, some of those architectural tests can be automated. And for that, we can use static code analysis tools. These tools process the system's source code and allow us to do some smart queries to analyze the system's health, the system's design's health. And there are many such tools on the market, but for demonstrations I will use Ndepend, as I have experience only of using this one. But again, everything I'm going to show you is relevant for all such tools. So what Ndepend does is it reads your source code, analyzes it, calculates lots of health metrics, for example, cyclomatic complexity, coupling, and many others. But the biggest problem, or may I say disadvantage, of using such tool is that it can be scary as hell to execute it for the first time. You run it and then you are greeted with all those graphs. Failed health checks. Everything is screaming red and you just want to close it, uninstall, and never see it again. So, of course, to use this tool effectively, you have to read its documentation. It includes over 100 predefined rules and health checks, and you have to understand what each means and to choose which ones are more relevant for your project. Moreover, you are not limited with those predefined rules, but you can use a query language, like in this example right here, to write your own tests that are verifying some metrics which are important for you. And of course, you can generate different graphs that visually describe the state of the system's design. For example, here we can see an example of a pretty high global complexity, because it looks like all these components are pretty much tightly coupled to each other. There are many references between them, and it's pretty hard, to trace the relationships between them. On the other hand, we have this diagram. And let's say here we are inspecting the inner workings of some module. So it's hard, to say whether its local complexity is high or low. We don't have many details here. But what we can say is that we can see a peculiar thing, a very interesting part right here on this side. And it's a coherent set of components which are very loosely coupled to the rest of this module, which means we can basically extract this part and make it a separate module on its own. Its local complexity will be for sure lower than the original one. The complexity of the original module will be reduced because we are simplifying it. And even the global complexity of the whole system won't be increased because, again, we are adding a module which is going to be very loosely coupled to the rest of the system. The weak spot of static code analysis is estimation of global complexity between microservices. It's challenging because microservices are usually implemented independently and often even in different languages and platforms, let alone different projects. What we can do instead here is to watch over the changes in those modules' public interfaces. For example, we can look for changes in the amount of public methods or message types emitted by some services. And when I say the word amounts, I don't mean that there is some absolute value, for example 10, like more than 10 methods is bad, less than 10 methods is good. No, there is no such magic number. However, we are interested in observing the trends, the changes in those values over time, how those interfaces are changing. If they keep growing bigger and bigger over time, it's probably a strong signal of a growing big ball of mud. Probably the local complexity of that single component is growing, and if you have too many connection points to the rest of the system, it's going to raise the global complexity of the system as well. And to observe such changes, we can integrate static code analysis in, for example, in our CI pipelines. Then, for example, end-depend for each build, it can calculate those metrics and build reports such as this one. And later we can watch over those reports, analyze them, and look for those microservices that are growing over their limits, that are increasing the complexity of the system. So until now, I spoke about how we should react to changes in architecture of the system. And in closing, I want to talk a bit about what are the drivers for such changes, what can cause our system to change over time. So first of all, organization that develops the software can affect its design. If, for example, we are working in a small company with, I don't know, 2 people in a garage, or maybe even 2 teams working in the same open space, then in such a case, the communication and collaboration between them is pretty easy. They can do away with some ad hoc integration. Somebody can say, hey, I'm changing this module, this is its new API from now on, and the other team members will just adopt. No drama, they can communicate pretty good because they are sitting close to each other. But on the other hand, if the company is growing, and for example, suddenly you have multiple buildings, or I don't know, multiple teams in different countries, or maybe one team, but it's a distributed one, people working from home. In this case, you will need to adapt your architecture for a more formal integration style, which means you will have to document the APIs and make sure that you are reducing the rate of changes of that APIs. Because again, each change of the public interface has to be communicated, and when the company is big, communication is not always easy. Second, the company that's going to use the software can change its own business strategy, and it can also affect our system design. For, all this time we are speaking about modules, but not all modules are equally important for the business. For example, the startup company that I told you about in the introduction, we had a module for managing and optimizing advertising campaigns. That was the core business of that company. That's how that company was making money. So it was crucial for the company to succeed, to implement this module correctly. On the other hand, we had some module which wasn't really important, like managing creative catalog, like managing files. Now, in domain-driven design methodology, usually those types of subsystems are called core subdomain and supporting subdomain. For core subdomains, you have to involve your most advanced techniques and tools, and for supporting subdomains, you can cut some corners here and there because usually they don't change much. However, the business strategy of the company may change, and as a result, the type of a subdomain will change as well. What has been supporting up until now can become the core business. And then in this case, you will also have to adapt its implementation strategy to meet the new requirements of the business. So that's what I wanted to share. Let's do a quick summary. So the goal of software architecture is to manage the complexity of the systems that we are building. We are doing it by dividing systems into components and thus dividing its complexity into local complexity, a complexity of each component, and global complexity, the level of interconnectedness between the system's components. Now, when the boundaries of those modules are bad, everybody is going to suffer from it. Therefore, we all have to look for symptoms of bad boundaries and react as fast as possible. Now, this requires a lot of discipline, and we can automate some of such tests using static code analysis tools. We can use them to control the evolution of the code base. And we have to be alert for changes in the organization that implements the software and for changes in the strategy of the companies that are going to use the software. And if the topic of evolutionary architecture is interesting for you, I recommend reading this book. It's called Building Evolutionary Architectures. And I think I have a minute for a few shameless plugs here. So first of all, domain-driven design. Who heard about domain-driven design here? Okay, I can see a few hands. That's great. For the rest of you, not long ago, I wrote a book called What is Domain-Driven Design? The idea is to give a short introduction to this methodology, and I really think it's really important today. It's important more than ever. And actually, this whole presentation I've been speaking about it without mentioning it explicitly. So, of course, I recommend reading this book. And if you do know what is domain-driven design and you want to hear some war stories about it, then about a year ago, a book called Domain-Driven Design, the first 15 years came out. In this one, I wrote a chapter about our case study of using domain-driven design in real life for 7 years. Also, I work in a company called Do It International. We are helping our customers to run their production workloads on cloud infrastructure. We are hiring all over the Europe, in UK, Germany, France. So if you're passionate about software architecture and cloud computing, check out our open positions. And if I didn't bore you to death yet, you can follow me on Twitter. And that's all I wanted to say, and we can go to questions.